Hi and welcome to this Leaving Cert Higher Level Forces video, and in this Forces we're specifically looking at pulley systems. So in this video we're going to look at pulley systems specifically from the higher level section of Applied Maths and look at how they're used in exam questions. So we're going to focus on understanding the idea of fixed versus movable pulleys, identifying all the forces acting on each particle, including friction. We're going to use Newton's laws of motion to find acceleration and tension, so specifically Newton's second law. And we want to understand how the accelerations of connected particles are related. We're going to work through some typical higher level exam questions with the focus being trying to find the familiar in the unfamiliar. I'm going to jump straight into higher level questions in this video. If you want more of an ordinary level or basic introduction, I've linked the introduction to forces and connected particles in the description below. We also won't be working with any inclined planes in this question. I worked that through separately in a different video, which is also linked in that description below. So we're going to look at some steps to approaching all force questions. So the first thing that you want to do is to draw a clear force diagram for each object or particle involved. We want to include all forces acting on it and show the direction of the acceleration, the direction of motion. Now, we have seen this in other sections, that idea of using your force diagrams. So I have linked some kind of connected material in videos below, specifically when we deal with work, energy, and power questions. There's a video that goes through that. And also when we're making our differential equations using force equations, I have a separate video that goes through that. What I will say is most of the steps here are going to be exactly the same. In a lot of our questions, they are going to ask us for force diagrams, but even if they don't, it's really important that you draw them because they're going to be helpful for you. Students who draw them will overall have less errors because they can really clearly see what's going on. That being said, I would always ensure that even if they weren't from an exam perspective, that you include all of your forces, even if they're not relevant to the movement. That means it keeps you in really, really good habits. So step 2 is, if required, resolve the forces into components parallel and perpendicular to the direction of motion. The good news is in this video, we're not going to have any resolving because we're only dealing with horizontal planes or straight pulleys. I have a separate video that goes through inclined planes where this step will be much more important, and that's linked in the description below. Step 3, for each particle, use the fact that perpendicular forces often balance. There is no acceleration in the perpendicular direction. The forces must be in equilibrium. So for example, upward forces equal downward forces. So usually what that means for us in these situations, weight equals reaction. That won't always be true, but we'll see it when we're working with horizontal surfaces. It will be true. So for each particle, focus on the direction of motion. So take the direction of the acceleration as positive and forces acting against that or in the opposite direction as negative. We're going to use Newton's second law, so F equals ma, where F is the resultant force. So that means adding anything that's in the direction of motion and taking away or subtracting anything that is going against it. Be careful when you're working with this. So all of our equations are going to be F equals ma, but I find it's easier that when you have your F, you write equals and then think about it as mass times acceleration. What that does is it really gets you thinking about what is the acceleration of this particle rather than just blindly subbing in A, which may not be correct. So for step 5, we're basically solving our simultaneous equations. We're going to end up with simultaneous equations in the majority of these questions. So sometimes we're working these through in ways that we are familiar with from maths, so an elimination method or a substitution method. And in some cases, we have nice quick shortcuts that we can use. So this is how we work with any force questions, our steps 1 to 5. So when we talk about our pulley systems, there's a few really important things that you need to remember. If you have one string, then you only have one tension. However, if you have two strings, we have two different tensions. Your options are to use things like T1, T2, or I prefer TS because I'm not a huge fan of subscripts, whatever works best for you. You just need to make sure you distinguish between them. Once the string goes slack, the particles no longer move as a system. And that's really, really important. What that really means for us is that if a string goes slack at any point, we need to recalculate an acceleration. The acceleration we get in these questions is an acceleration of the connected particles, it's of the system. So as soon as the string goes slack, then the particle is no longer moving under that system and has a new acceleration. So when you're working with questions with movable pulleys, ensure you take account of the different accelerations. As soon as there's a movable pulley, we need to really consider our accelerations, and there's going to be two main types of questions that we're going to see. Most students understand the basic versions, but the trick is trying to find that familiar one of those two scenarios in any of our other questions. Just a note on acceleration, put the acceleration in the easiest direction possible if you don't know the actual direction. The reason is, even if you're wrong, that acceleration will simply come out as a negative. Okay, so if you put the acceleration the wrong way, our acceleration will simply work out as a negative value, telling you you have it in the wrong direction. My only caveat to that is our friction force, which we'll talk about later in this video, will always oppose motion. So it's really important that if there's a friction force involved, that you do have the correct direction, because the friction will be going in the wrong direction, which is a much bigger issue than this acceleration piece. So watch out for friction. If there's friction involved anywhere in the question, then you need to be very, very clear what direction the whole system is moving in. So what do we actually mean by a fixed pulley? So you can see here, if we have a weight that's pulling another weight and we apply a force in that direction, the weights or particles move, but that pulley remains fixed. So we have what is often called a light fixed pulley, which means that that pulley doesn't have mass, so we don't take it into account in our calculations. If it doesn't have a mass, we don't care about it. So we also are told we have a light inextensible string. All that means is that there's no give in that string. Again, light means no weight. And the difference here is if we're dealing with something like Hooke's law, we'll see that we have what's called an elastic string. So if you see a question and it tells you that there is an elastic string, then we're getting into Hooke's law. I've linked the video for Hooke's law below if you want to go into that in more detail. For all of our questions today, we're looking at light inextensible strings. So for our fixed pulley, the particles are moving, but the pulley stays in the same place, and the force is applied to one end of the rope. So that may be one weight is heavier than the other, and there will be a movement. When we have a situation like this with the fixed pulley, both particles have the same accelerations. So you can see here with those blue arrows and the A, that is telling us that the acceleration is the same. Now, with movable pulleys, we have two different scenarios. So here we have what's called a movable pulley that is fixed on one end. So you can see here on the left, the string itself is stuck in place and it can't move. The pulley here, so this pulley is a movable pulley. It's going to move up as this particle here moves down. We also have a fixed pulley, which we can see attached up here. So when we have a movable pulley, we will also have fixed pulleys as part of the question. What the big difference for us and what you're going to see is that the movable pulley will have a mass. So the question is, what is our connection between these accelerations? The easiest way to really think about this and figure it out, especially if you're looking at one of these questions in June, having not seen it for a while, is to look at the length of strings. So if this moves up by 1 meter, it will go 1 meter in string here and 1 meter of string here, which effectively means that this will have to go down by 2 meters, because for that 1 meter of lifting up, it releases 2 meters of string. And that gives us a really good sense of our acceleration. This acceleration here is going to be A, while this one here is going to be our 2A. So we can see as that moves down, it's going to move down a lot more than what we see the movable pulley move up. So this is an A2A acceleration question where it is fixed at one end. If you have any question that is a movable pulley question where it is fixed on one end, that is what you're going to see. And throughout this video, we're going to see lots of different versions of this that may not mimic exactly what we see here, but are still going to represent a movable pulley with that is fixed at one end, where we see an acceleration of A and another acceleration of 2A. The second movable pulley situation that we see is a movable pulley that can move at both ends. So in this case, both ends are free to move. Now, one thing to say about these movable pulley questions where it is free to move at both ends, for you to make your life as easy as possible, it's a good idea to make sure that the two outer pieces always move in the same direction. Even if that is not necessarily what is going to happen, it's important that you do that. It's going to simplify our question hugely, and we don't have to get signs or anything involved. And if one of those is the wrong direction, remember all that's going to happen is our acceleration will come out with a negative, indicating to us that it's in the opposite direction. The reason that it's so important that we do that is because all of these three particles have different accelerations. None of them share the same acceleration. How we show this is through an average. We will say that the one on the left has an acceleration of A, the one on the right has an acceleration of B, and then our movable pulley in the middle has an average acceleration of the two, A plus B over 2. Be careful with that direction. Make sure the direction of the movable pulley makes sense. Other than that, like I said, if those accelerations or those directions are incorrect, they're just going to come out with a minus instead. So either put both of them going up on the outside or both going down. Again, that may not be what actually happens. You may find that in a situation, the left one goes up and the right one goes down. But if that happens, all that's going to happen with your answer is you'll find maybe B is a negative number. So this is the question from the 2024 paper, question 2, part B. A student sets up a pulley arrangement shown in the diagram. A light inextensible string passes over two smooth fixed pulleys and under a smooth movable pulley of mass 6.3 kg. Weight 1 is equal to 24.5 newtons. It's attached to one end of the string, and weight 2, 44.1, is attached to the other end. The system is released from rest. Show on separate diagrams the forces acting on the pulley and on each of the weights while they are moving. So the first thing we need to do in a situation like this is we want to look at what way all of these particles will move. We have here a situation of average acceleration, so it's important that the outer two pieces move in the same direction. So it doesn't matter if these are going to move the wrong way, because all that's going to happen is you're going to find that your answer will end up being negative. So I'm going to say that this is moving down with acceleration A, this is moving down with acceleration B, and then this one is going to move up with acceleration A plus B all over 2, an average acceleration. Just a few things to note here when we're working. They've given us the mass of the movable pulley, 6.3 kg, but they've given us the weights of 1 and 2. So remember that our weight is equal to mass times gravity. So therefore, to get your mass, we can do weight divided by gravity. What that means is then for weight 1, which is 24.5 newtons, we can get the mass by doing 24.5 divided by our 9.8. And that works out as 2.5 kg, which we're going to need later on. And it's worth kind of adding to your diagram for yourself. And that's like mass 1. So then on weight 2 is 44.1 newtons. So the mass of the second one is 44.1 divided by 9.8, which works out as 4.5 kg. So we can add that to your diagram as well. So use your diagram so that it's as helpful as possible for you. So then when we get to part 1, show on separate diagrams the forces acting on the pulley and each of the weight while they're moving. We now have the direction of motion and the accelerations, which will make this much easier. So let's start with weight one. So for weight one, we're going to have the force that's pulling it down. This is our weight. So our weight one, which is equal to 24.5 newtons. I'm going to just add my 2.5 kg into my diagram here. So I have it. And then pulling it up is the tension in the string. I also then have an acceleration of A that's pulling it down. Then for my movable pulley of 6.3 kg, we have our weight that's pulling it down. Weight is mass times gravity. So the weight of this one is 6.3 times 9.8, which works out as 61.74 newtons. And then pulling it up, we have two tensions. Remember, our direction of motion for this one was pulling up, and this is A plus B over 2, an average of the other two accelerations. And then we have our weight 2. So pulling that down, we have its weight, which we don't need to calculate because it was given to us in the question. We do need to remember that its mass is 4.5 kg. And then pulling it up, we have our tension. This is moving down with an acceleration of B. So then we're going to work through the force diagrams, through each of the diagrams to make a force equation. So I'm going to call this force diagram 1, 2, and 3. So our three force equations are going to be, so number 1, we're always going with the direction of motion. So we have 24.5 minus our tension is equal to our mass times our acceleration. For number 2, our movable pulley, it's moving up. So we have two tensions pulling it up minus its weight that's pulling it down because it's opposing the motion. And that is going to be equal to mass times its acceleration, which is A plus B over 2. And then for number 3, we're going to have our working downwards. So our weight is pulling it down first. 44.1 minus our tension is equal to 4.5 times B. I find having those directions of motion are key, but including that acceleration as A, B, and A plus B over 2 is going to make this so much more helpful. So when we have a situation like this with an average acceleration, the easiest thing to do is to isolate your A, which in this case is going to be 24.5 minus T all over 2.5. And then with equation 3, let's isolate our B, which is going to be B equals 44.1 minus T all over 4.5. And then we sub that into equation 2. So we get two tensions minus 61.74 is equal to, I'm going to divide in that 2 into the 6.3 before we do anything with it because it's going to make life just a little bit easier. So that's going to give us a 3.15. 3.15, and then we're going to do A plus B, which is going to be 24.5 minus T over 2.5 plus 44.1 minus T over 4.5. So we now have an equation that just has T's, and we're going to be able to work through that. There's so many different ways we can use to solve this to get our answer of T. One of the ways I like to do this is actually cleaning up those fractions on the right-hand side into individual fractions or decimals. So for example, 24.5 divided by 2.5 actually gives us 9.8 minus. This gives me T over 2.5. So if you have 1 over 2.5 and your calculator can help you with that, that effectively gives us 0.4t. So that cleans up that fraction into something a lot more manageable. Doing that with the second fraction as well, we also get 9.8, and then we get a not so nice fraction. So I'm not going to change this one into a decimal. It is 2 over 9. So rather than doing any rounding, I'm going to leave it as is. So then we can come along and do a little bit of tidy up in that bracket. And what we'll be able to do is 9.8 plus 9.8 is 19.6 minus 0.4 minus 2 over 9. Again, that calculator will help you out with this, so you're not trying to do a lot of mental maths. It gives us 28 over 45. I am going to leave that in fractional form. And then we can multiply out the bracket. I particularly like this method, but you are absolutely welcome to either make a common denominator, multiply out that 3.15, whatever way works to get the t on its own. For me, I feel that this is one of the most efficient ways that we can work. So we get 61.74 on this side as well. When we multiply this out, we get a 1.96 t. So leaving that as a fraction earlier has made that much nicer and cleaner. So that gives me 3.96 t is equal to 61.74 plus 61.74, which is 123.48. And then t is going to be 123.48 divided by 3.96, which gives us 31.18 newtons. So that's a nice, in my opinion, kind of quick way to work through it. But whatever algebra method you want to go from that top line, and that gets you to that answer of tension. This is the question for part B from the 2007 paper, higher level paper. So a light and extensible string passes over a small fixed pulley A and under a small movable pulley B of mass m kg. I'm actually going to just write in that m. So we have it there. And then over a small fixed pulley C. So A and C, we actually don't care about. They're fixed, they're not doing anything. A particle of mass 4 kg is attached to one end of the string and a particle of mass 6 kg is attached to the other. The system is released from rest. So we need to understand, how is this moving? Now, obviously we don't know what M is, so we just need to make a decision on the direction. So I'm going to decide that this is moving down. If you do it the other way, there is absolutely no issue. If that middle one moves down, that means our outer two move up. Remember, we always want these outside two to go in the same direction. So this, I'm going to say, has an acceleration of A. This one I'm going to say is B, giving this middle one an acceleration that is an average of the other two. So like I said, there's no like rhyme or reason here for that direction. We don't really know what M is, so we can't really make a decision, but there's no friction or anything involved, so it doesn't actually matter. Once we are going in a direction that makes sense for the movement, we'll be fine. If we get this wrong, remember our acceleration simply comes out as negative. So on separate diagrams, show the forces acting on each particle and on the movable pulley B. So let's start with our first one, which is our 4 kg mass, and we always have weight. So weight is equal to mass 4 times gravity, 9.8, which is going to give us a 39.2 newtons. We then have a tension that's pulling it up, and we've said that that direction of motion is upwards with an acceleration of A. We then have our movable pulley B that has a mass M. So there's my B, and it has a mass M. So it has a weight pulling it down. Its weight is mass times gravity. So we're going to write that as W is equal to 9.8 M, and then pulling it up, it has two strings, so it has two tensions, and we have decided that that's moving down, which is going to have an acceleration of A plus B over 2. And finally, we have our 6 kg mass. It has a weight pulling it down of mass 6 times gravity 9.8, and that's going to give us a 58.8 Newton force, and pulling it up is tension, and that direction of motion is upwards with an acceleration of B. So we're going to make our force equations. For each of them, we're using the idea of F equals ma, F being the resultant force taking the direction of motion as positive and anything going against it as negative. I'm going to call this 1, I'm going to call this 2, and I'm going to call this 3, just because the two particles the 4 kg and 6 kg don't have names the way that B does. So I'm just going to call them 1, 2, 3. And this becomes T minus 39.2 equals 4A. And then equation 2, it's going down. So we have weight, which is 9.8 m minus 2t is equal to m times a plus b over 2. So I've kind of run out of space. So I'm going to do it down here. So for 2, we're going to have 9.8 minus 2t is equal to m times a plus b over 2. And then for equation 3, which hopefully is a nice short one, we're moving upwards. So we have t minus 58.8 is equal to 6b. So there are 6 equations. So our next step is for part 2, find in terms of m the tension in the string. So what I'm going to do first is I'm going to work these the way we always work these average acceleration questions. I'm going to get my A on its own. So I'm going to isolate my A. And then I'm going to isolate my B. And then I'm going to sub them in. That works out to be one of the easiest ways to do these questions, but any algebra way is absolutely fine. So then for equation 2, we get 9.8 m minus 2t is equal to m over 2. I'm pulling that 2 out. That way I have an a plus b that's a little bit easier to look at. So they're already fractions. Plus b, 58.8 all over 6. I find one of the easiest ways to work this is to kind of break out my fractions if I can. So I'm going to leave this as m over 2. So then t divided by 4, that's a quarter t or 0.25 t. Minus 39.2 divided by 4 gives me minus 9.8. Plus t over 6, that's 1/6 t. Doesn't give me a nice decimal, so I'm going to leave that as a fraction. And then minus 58.8 divided by 6 is minus 9.8. So tidying this up a little bit gives us m over 2. In terms of my tension, 0.25 t plus 1/6 is literally 5/12. The calculator can help you do that really nice and quickly. And that's 19.6. And then I'm going to try get one more line in here. I'm going to multiply in that first fraction. So that gives me 5m over 24t minus 9.8m. So now I have something a little bit nicer. And what I'm going to do is try and isolate my t's. So I'm going to get my t's to one side. So that's 5m over 24t plus 2t, bringing those to the right. And then I have a 9.8m plus 9.8m, which is 19.6m. I'm going to pull out my t, leaving it 5m over 24 plus 2. And that equals 19.6m. Before I divide that across, I am going to make this into a single fraction. So I'm going to say that's 5m plus 48 all over 24. So all I'm doing there is I'm saying that 2 can be written over 24, but I also need to multiply the top by 24, which gives us that 48. And that gives me my 19.6m. That makes it easier to bring across that 24 to multiply first, and then divide by the 5m plus 48. Final answer is going to be 470.4 m all over 5m plus 48. And if you left your answer in terms of G, that's fine. You'll get 48 mg on that top line instead. The bottom line will be the same. So part 3 tells us if m equals 9.6 kg, prove that pulley B remains at rest while the other 2 particles are in motion. So I've just pulled through our expression for t from our previous part. And then this is the acceleration of the 4 4 kg mass, and this is the acceleration of the 6 kg mass. Remember, we have already decided that these were moving up and that was moving down. So we had our A, our B, and our A plus B over 2. So first thing we're going to do is we're going to work out our tension given that M equals 9.6 kg. So we're going to come along and we're going to sub that in. And when we do that, we're going to get T equals 470.4 times 9.6 all over 5 times 9.6 plus 48, which gives us a tension of 47.04 newtons. We can then work out our acceleration by subbing in our 47.04 minus 39.2 all over 4, and that gives us 1.96 meters per second squared. For B, we get 47.04 minus 58.8 all over 6, and that equals minus 1.96 meters per second squared. What that means is for particle B, or movable pulley B, we are going to have an acceleration of A plus B over 2, which is going to give us 1.96 minus 1.96 all over 2, which gives us 0. Therefore, B remains at rest. So we just need to be very clear that the acceleration is equal to 0. So this is question 4B from the 2009 higher level paper. A mass M1 kg is at rest on a smooth horizontal table. It is attached to a light inextensible string. The string, after passing over a small fixed pulley at the edge of the table, passes under a small movable pulley C of mass M2 kg. The string then passes over a smooth fixed pulley and supports a mass of 1 kg. The system is released from rest. So the first thing we're going to do before we look at the question is look at how this system is going to move. So the most obvious one here is our M1. It will have to move to the right. There's nothing that would pull it to the left. So this one we're going to give acceleration A, and it's to the right. Because we have a movable pulley, the scenario we're looking at is a movable pulley that is moving at either end, which means we're looking at an average acceleration. So we want that 1 kg mass to move the same way as the M1. What that really means is if the M1 is moving towards the movable pulley, the 1 kg will also have to move towards the movable pulley. So it's moving upwards, and it's going to have a different acceleration. Its acceleration is B. That means our movable pulley C is going to move down with an average acceleration of A plus B over 2. So this is an average acceleration question, but it's not the traditional type where both ends are hanging, and it doesn't have to be. So it asks us in part 1 to find in terms of M1 and M2 the tension in the string. So even though it doesn't ask for it, we are going to do our force diagrams in order to get our force equations and then find our tension. So let's start with our M1. So this is our mass 1. It has weight acting down. So I'm going to leave my weights in terms of G, but you absolutely can plug in for G if you like. We don't have a lot of numbers in this question, so sometimes with that kind of question, leaving them in terms of G is a little bit easier. We then have a tension pulling it to the right and a reactionary force here that will be equal to its weight, M1G, but because there's no friction, that's not really important to us. We are moving to the right with an acceleration of A. Then we move on to our movable pulley. So our movable pulley is C, and C has a mass of M2. So its weight is going to be its mass, M2 times gravity, G. We then have two tensions pulling it up, so T and T, and we have decided that this is moving downwards with an average acceleration of A plus B over 2. And finally, we have our 1 kg mass, and it is it has got a weight of mass times gravity, so 1 times g, or just g, and then pulling it up is tension, and its acceleration is upwards, and we've labeled that B. So in order to make our 3 force equations, we work using F equals ma, and our first equation, I'm going to take it from this, our second I'll do from here, and our third from here. So equation 1. Because it's moving to the right, the only thing pulling it to the right is tension. There's nothing pulling it to the left. So tension is equal to mass 1 times its acceleration, which is A. So then for 2, our movable pulley, it's moving down. So what's pulling it down is its weight, M2G, minus 2 tensions is equal to M2A plus B over 2. And then equation 3 is going upwards. So we start with our tension minus our weight, which is gravity, which is mass times acceleration, 1 times B, which is simply B. So now that we have our 3 force equations, we're going to go through this as normal. We're going to isolate our A, which is just T over M1, and B is already isolated. We're then going to work with equation 2, and we're going to have M2G minus 2T. I'm going to pull out that 2 in front of the bracket, leave me with just A plus B, which is giving us T over M1 plus T minus G. So what I'm going to do is I'm going to multiply everything by 2m1. So we'll do 2m1 on both sides. So that 2 effectively disappears on that right-hand side. Over here we get 2m1 m2g minus 4 m1t is equal to m1 by m2 by t over m1 is just going to give us m2t. And then m1 by m2 by t is going to be plus m1 m2t. And m1 by m2 by minus g is going to give us minus m1 m2g. So we're going to get all of our t's on one side. So that's 4 m1t plus m2t plus m1 m2t, and then everything else on the other side, that's going to be a 2 m1 m2g plus m1 m2g, and that combined is going to give us a 3 m1 m2g. We can pull our t out, highest common factor, 4 m1 plus m2 plus m1 m2, and then t is going to give us as an answer 3 m1 m2g all over 4 m1 plus m2 plus m1 times m2. And that's our answer for t in terms of our m1 and m2. So part 2 tells us that the pulley C will remain at rest if 2 over m2 minus 1 over m1 equals k. Find the value of k. So the trick here is to focus on what they told us about pulley C being at rest and not to panic about what they've given us until we have an expression of our own. So if pulley C remains at rest, that means that A plus B over 2 equals 0. What that means for equation 2 is we're going to have mass m2 times its acceleration, which is 0. So that's simply going to leave us with an m2g minus 2t, and that's simply going to equal 0. So what we can do then is bring over the tension and then sub in our value of t in terms of our m1 and our m2 that we worked out in the previous part. That is 3 m1 m2g all over 4 m1 plus m2 plus m1 m2. And now we have an expression with just m's, and what we're trying to do then is effectively get this looking like the thing that the question has given us in part 2. So first thing I'm going to do, I'm going to divide both sides by an M2 because it appears on both sides. And then to get rid of a fraction, I also am actually going to get rid of a g at this point, so divide both sides by g. Now I'm going to remember that this has a 1 still here, so I'm going to bring my denominator from the other side up, and I'm left with 4m1 plus m2 plus m1 m2, and that's going to equal to 6m1. So if I bring that over, that's 6m1, I get minus 2m1 plus m2 plus m1 times m2 equals 0. I don't want to start with negative, so I'm going to change my signs. So I'm left with something like this. Now, we want fractions with an m2 and an m1 on the bottom. I can see where the 2 is. I can see a minus and a 1 effectively, but I'm going to need to get rid of some m's. So what I'm going to do is I'm going to divide this by m1 and m2. What that's going to do, it's going to get rid of the m1 that's on top and leave me with an m2 on the bottom, which is exactly what we want for that first term. Remember, if you do it to one term, we have to do it to every single term. And what we're left with then is something that looks a lot closer to what they've given us, which is 2 over m2 minus, oh, wrong one. So it's m2 on the bottom and m2 on the top. So 1 over m1, perfect, minus, these all will divide into each other, leaving us simply with 1. The only thing I need to do is bring that one across. And what that does is it gives us a value that k is equal to 1. And that's our answer. So sometimes these look and feel a lot harder than they are. The practice here will really help, but our focus should be on getting an answer and then making your answer look like what they gave. The hardest or most common error is students trying to start with that answer, which will tend to lead you in circles. So friction force is something we see quite a lot in all of our exam questions. A friction force is one that opposes motion, and that's really important. So for us to do this correctly, we always need to know what direction a particle is moving in, then we can correctly apply our friction. When two objects are in contact, friction will be a specific coefficient, which we call the coefficient of friction, and the symbol for that is the Greek letter mu. So we can see it down here. So that's our mu. That mu is specific for two different objects. So for example, a table does not necessarily have a coefficient of friction. The coefficient of friction is between the table and a specific particle. That means that different items on the table will end up having a different coefficient of friction with the table. So that coefficient of friction has to be between 0 and 1. We have an idea of kinetic friction and static friction, which basically means friction when it's not moving. So to kind of get it to move versus friction when it is moving. We don't distinguish between that in applied maths, but just if you did see it, that you are basically talking about the same thing, but it's always harder to get a body to move over friction than if it's already moving for friction. So they just are slightly different coefficients of friction. Like I said, for applied maths, we don't worry about that at all. So we have a formula from page 57. It is the coefficient of friction mu is equal to F over R. So that is your friction force divided by your reaction force or your normal reaction. And an easier way to kind of rewrite that for all of our questions is friction is equal to mu times R. Just another note about mu, because it is the force of friction divided by the reactionary force, that's newtons over newtons. The coefficient of restitution doesn't have any units, it's unitless. And I mentioned that for any work you might have to do with dimensional analysis. This is question 4A from the 2022 deferred paper. A taut-light inelastic string is fixed at one end and passes under a movable pulley P of mass 4 kg, which hangs vertically. The other end of the string is attached to Q, a mass of 4 kg, which lies on a rough horizontal surface. So a few things to bear in mind. We have that rough there, meaning we're going to have to deal with friction. A second inelastic string connects Q to R on a mass of 10 kg, which hangs vertically. The fixed pulleys are smooth and light, and the coefficient of friction between Q and the surface is a half. The system is released from rest. Find the acceleration of P, Q, and R in terms of G. So the first thing we want to do is understand how is this moving. So it doesn't tell us, but given that this here is a 4 kg mass, and this is also a 4 kg mass, the 10 kg will drag all of this down. So this one will move to the right, and this pulley will move up. Now, this is a movable pulley that's fixed at one end, meaning our acceleration is an A to A situation. So if we just focus on P and Q for a second, the acceleration of A is P, or the acceleration of P is A, and the acceleration of Q is 2A. Now, if you focus on Q and R, they will have to move with the same acceleration, meaning that this is simply going to be 2A. So we can look at this in two parts. Just bear in mind that we do want our answer in terms of G. So rather than filling in our 9.8, we're going to be filling in G in all of our equations. The other thing to note is we have two strings, which means we're going to have two different tensions depending on which string we're working on. That can be either listed as T1 and T2 or T and S. So although they didn't ask for it, our next step is going to be doing some force diagrams before we do our force equations. So let's start here with our particle P. So this is P. Remember that that is 4 kg. It is helpful to have the mass in there. We have a force pulling it down. That is weight. So that is mass times gravity. Remember, we're not subbing in for gravity this time because they want that answer in terms of G. So then pulling it up, we have two bits of string. So we have two tensions pulling it up. Then remember our direction of motion is upwards, and that is our A. Next, we're going to work with the 4 kg. So this is particle Q, and it's 4 kg. We have weight pulling it down, which is mass times gravity, so that's 4g. We have a tension pulling to the left, which we've already called T, so bear that in mind. That on our P, that was T and T, and we also had the same string over to the left, which was T. Then we have one to the right, and we're going to call that S. Now you can call that T1 and T2 if you prefer, and that's going to be the same tension connected to our OR. So just be very careful that you do distinguish between the two tensions. We then also have a reaction. So our reaction is going to be equal to the weight, which is just 4g. And that's because there's no up and down movement. The movement is all horizontal. So this is our movement, and the acceleration is 2a. Now remember, we have a rough horizontal surface, so we need to understand the order or the way that this particle is moving in order to understand friction, because friction always opposes motion. Because it's moving to the right, then friction is pulling it to the left. So our friction is going to be equal to mu times R, which is going to be a half times 4g, which is going to be 2g. And that's complete for that particle. Next, we have our last particle, which is R. R is 10 kg. So we have our weight pulling it down. Again, remember, we're leaving everything in terms of G. And then we have a tension pulling it up, which remember is our S. We then have acceleration that's pulling that down, and its acceleration is 2a. So now for each of those diagrams, we can make a little force equation. So let's start with P. P is working upwards, so we have 2t minus its weight, 4g, is equal to mass, which is 4 times its acceleration, which is a. Then we have our Q. So Q is moving to the right, meaning we get S minus my friction, which is 2G, minus T, and that is equal to our mass, which is 4, times our acceleration, be careful, that is 2A. So that gives us S minus 2G minus T is equal to 8A. And then finally, we have or. Again, or is moving downwards. So we're taking our 10G first as positive minus our S, and that is mass times its acceleration, which is 2A. So that is 10G minus S equals 20A. Now, this is going to work out quite nicely for us if we look at equation 1, equation 2, and equation 3, we can actually work all three together at once. Now, there's a very special reason why we're allowed to do this. So the first thing I'm going to do is I'm going to divide equation 1 by 2, leaving me with t minus 2g is equal to 2a. We then have S minus 2G minus T equals 8A. And then finally 10G minus S equals 28. Now the reason we can do all three together is when we do all three together, it is going to get rid of not one, but two of our unknowns. So if that was only going to get rid of one, that wouldn't be a correct method, because then we would be stuck with an equation with two unknowns and nowhere to go with it. So the only reason we can do that in this case is because our three equations together will get rid of two unknowns. So this is going to leave us with 6G, and that equals 30A. So then my A value is going to be 6G divided by 30, which is 1/5 G, and that's meters per second squared. Now that's our value of A, but remember they want the acceleration of P, they want the acceleration of Q, and they want the acceleration of R. Make sure these are all clearly labeled. So this is going to be 1/5 G meters per second squared. Q then is 2A, which is going to be 2/5 G meter per second squared, and R is also 2A, which is 2/5 G meters per second squared. And again, if you want to write that G on the top line, so 2G over 5, that's absolutely perfect. So here is our final answer in terms of G. Now, if you worked it through and accidentally subbed in your G's along the way, you'll get your answers as numbers. So that will be 1.96 and 3.92. So let me put an example here. So you might get for A 1.96 meters per second squared. So then all you need to do to convert that back to having a G is divide that by 9.8, and that's going to give you a fifth and or 0.2, whichever way you want to work it. So 1/5, and then you put your G back in, and we're back to having the same answer. So if you accidentally subbed in your G earlier on in the question, you missed that in terms of G piece, it's absolutely fine to just divide it out there at the end. So a block A of mass 8 kg and a block B of mass 4 kg lie at rest on two rough horizontal tables. That rough is important. It's telling us that we are going to have friction involved. The coefficient of friction between A and the table it lies on is mu A. The coefficient of friction between B and the table it lies on is mu B. So mu B is equal to 2 mu A, that's important. And the blocks are connected by a light, inextensible string which passes under a smooth, movable pulley of mass 12 kg. After the system is released from rest, the blocks and pulley move and the string has a tension of 32 newtons. Okay, and that's important. So tension of 32. So when the system is released, we can make a good assumption that these A and B blocks are going to move inwards and our pulley will move downwards. Bear in mind, when we have a system like this, the acceleration of one will be A and the second one will be different, so we call that B. And then the pulley in the middle, because it has two strings, is going to have an average acceleration. So that's A plus B over 2. It's always good to put that direction of movement on your diagram from the start because it is really going to help you. Even though the question didn't ask for it, what we're going to do is create some force diagrams to help us with this question. So here's our 8 kg mass, which is A. And the first thing that it has is weight, and weight acts downwards, and that's going to be 8g. The next thing we have is the tension in the string, which is pulling it to the right. We also have the reaction, which in this case, because it's lying on a horizontal table, is just going to be equal to the weight. The direction of movement is to the right. So there's our A. That also helps us understand that friction, which opposes motion, then must be going here. So our friction is equal to mu, and in this case, it's mu A times R. Okay, and for us, that's actually going to be mu A times 8g, because that's our reaction. Okay, for the pulley, we have 12 kg, so its weight is equal to 12g. It then has two tensions pulling it up, so T and T. And as we said, our movement is downwards, and it's going to be an average of both of the particles on the table. Then we have B, it's 4 kg, so its weight acting downwards is 4g. It's got a tension, which is in this case pulling it to the left. It then has a reaction, which is equal to its weight because it's on a horizontal table. Its direction of motion is to the left, and that means its friction is opposing motion. Actually, I might just pop the reaction on the other side. So that is 4g. So we have enough space to do our friction, which is mu R. So that is mu B times R, which is going to be mu B times 4g in that case. So then what we want to do is we want to create an equation for each of these force diagrams. So the direction of motion is telling us which way we're taking as positive. So for the first particle, we'll take the A, that's our 8 kg particle. We're going to have tension. Take away the friction, which is mu A times 8g, and that is equal to ma. So we're using F equals ma. So the force, the resultant force is mass times acceleration. So the 8a. The second one, let's do our particle B. So it's moving to the left. So bear that in mind. Now things to the left will be taken as positive. So we have T minus mu B for G is equal to mass, which is 4, times our acceleration, which is B. And then lastly, 3 is going to be our pulley. Our pulley is moving down, so we take down as positive. So that's 12g, take away 2t, and that's going to be equal to 12 times a plus b over 2. Now what we're trying to find is mu b. But remember that they actually gave us 2 bits of information that we can use to help tidy up a little bit. That is mu B is 2 mu A, and tension is 32. So let's put in the tension. So that's 32 minus, here I'm getting 8g mu A, and that equals 8a. And here we get 32 minus 4g mu b is equal to 4b. And here we get 12g minus 64 is equal to, and I'm going to tidy that up as to 6a plus b to get rid of our fraction. Now, because we want to find mu b, it would be much better for us if we replaced mu A with mu B. So mu A is equal to, sorry, mu B is equal to 2 mu A. So we can rearrange that into being, well, mu A is equal to a half mu B. So we can put in a mu B in here with a half. So let's get ourselves some space and sub that in, and then let's work through the algebra. So that's going to give us 32 minus 8g and then a half mu b, which we're going to be able to tidy up as into 32 minus 4g mu b is equal to 8a. So let's take a look at the equations we're working with. So we have 32 minus 4g mu b is equal to 8a. We also have 32 minus 4g mu b is equal to 4a. 4, it should be b, 4b. And if you look at the left-hand side of both of those, you'll see that they are now equal. What this means from these two equations, we can say that 8a is equal to 4b, or 2a is equal to b. So that's an important little idea that we now have. So then if we come along to equation 3 is 12g minus 64 is equal to 6a plus b. Now if I rearrange, or if I sub in instead of b to a, we now have an equation where we can solve for a. So let's get rid of that g, so that's our 9.8. So 12 by 9.8, that gives us 117.6 minus our 64. That's giving us 53.6. And that equals 6 times 3a. So that gives us 18a is equal to 53.6. Dividing both sides by 18 is going to get us to a is equal to 2.97 meters per second squared. B is then going to be 2 times that. So if we just double that number, we get 5.95 meters per second squared. We're still not quite there. We now need to go back and get mu b. Doesn't matter if we work with equation 2 or equation 1, because they're going to give us pretty much the same thing. So let's work with 2 because it's here. So we have 32 minus 4g mu b, remember that's the thing I want, is equal to 4 times b, which is 5.95. So if I multiply that by 4, that gives me 32 minus 4g mu b is equal to 23.82. So just giving us a bit more space, we get minus 4g mu b is equal to 23.82 minus 32. So mu b is going to be this answer. Let me throw in the calculator, divided by minus 4 times 9.8. I'll actually just put the whole thing in while we're going. So mu b equals 0.2086, so 209. And then in turn, we could work out our mu a if we needed to. So part 2 then asks us to calculate the acceleration of the movable pulley. So as we had on our diagram, the acceleration of the movable pulley is going to be the average of the other two, so a plus b over 2. That's our a and that's our b. You can change that to being a plus 2a, whatever works best for you. So our acceleration is going to be 2.97 plus 5.95, all divided by 2. This gives us 4.46 meters per second squared. This is the 2014 higher level paper question for part A. A block A of mass 4 kg can slide on a rough horizontal table, so that's important. We're going to need to bring friction in here. It is connected inelastically to a pulley system from which B, a mass of 8 kg, hangs freely under gravity by a light inelastic string as shown in the diagram. A horizontal force P of 320 newtons is applied to the mass A, which then moves in the direction of P. The coefficient of friction between A and the table is 4/7. Find the acceleration of A and the tension in the string connected to B. So the first thing we always want to do is understand what way this system is moving. So they tell us in the question that a horizontal force P of 320 newtons is applied to mass A, which then moves in the direction of P. So that's really important for us to note. So this force is going to cause a movement of A to the right, meaning that B is going to have to move. Now, in terms of our acceleration, what we effectively have is this is a movable pulley. It is connected to A, so it's allowing A to act like a movable pulley. It's a movable pulley that's fixed on one end, meaning we're going to have an A to A acceleration. Because there's two strings here, that means the acceleration of A is going to be A, and the acceleration of B with only one string is going to be 2A. Remember, the logic to use for that is every time that A moves a meter, it is effectively taking 2 meters of string from B. That's why B has double that acceleration. So that's a great way to kind of make sense of it. So even though the question doesn't ask for it, we are going to draw out our force diagrams to help us to finish the question. So let's start with our particle A. Particle A has a mass of 4 kg. All particles have weight, so weight is equal to mass times our gravity, which works out as 39.2. We also then have a force pulling it to the left. Just remember that this movable pulley that we have here is connected to A, so that's all one piece, meaning the force that's pulling it to the left is got to do with these two strings, so there is 2T that's pulling that there to the left. We also have a pulling force here to the right, which we're told in the question is 320 newtons. And we have our reaction, and because there's no up and down movement, we can go straight to reaction being 39.2 newtons. So our direction of movement is to the right with an acceleration of A. And don't forget that this table is a rough table, so we're going to have to take into account friction. So our friction is calculated as mu times R, where mu is given to us in the question as 4/7, and our R is 39.2. So that works out for us as 22.4 newtons. And there's no other forces acting on that particle A. Then we move to particle B, which has a mass of 8 kg, and the forces acting on that are weight, which is mass times gravity, which is 78.4 newtons. And then pulling it up is tension, and the movement here is upwards with an acceleration of 2A. So now let's work with our force equations. We're working with F equals ma, Newton's second law. We then can work with particle A. Remember, we only take forces that are in the direction of motion. So in this case, horizontal forces. Any perpendicular forces, so in this case, vertical forces, are ignored. Anything that goes in the direction of motion, we take as positive, so that's 320. And then anything against motion, we take as negative. So minus 2t minus our friction is equal to mass times our acceleration, which in this case is just A. It's a really good habit to get into to talk about that as mass times acceleration rather than ma when you're filling it in, because you may end up filling in A automatically when that's not actually what the acceleration is. So just take a lot of care with that. So I've just tidied up that equation, and that becomes our equation 1. We then have our second particle, particle B. Its motion is upwards, so anything upwards is positive, minus anything downwards is going to be our negative. Mass then is 8 times its acceleration is 2a. So you can see here, if you were just going ma, it'd be very easy to accidentally fill in a. While if you say mass times acceleration, that acceleration is 2a. So we now have t minus 78.4 is equal to 16a, and that becomes equation 2. Now we have two equations with two unknowns. Let's solve these simultaneous equations. So 297.6 minus 2t is equal to 4a. I'm going to double this second equation straight away. So that gives us minus 156.8 is equal to 32a. What that does is it means that our 2t minus 2t are now eliminated. That gives us 140.8 is equal to 36a. A is then 140.8 divided by 36, which gives us 3.91 meters per second squared. That one is recurring, but it's not going to affect our rounding. That is our acceleration of A. They didn't ask for it, but the acceleration of B would simply be 2a, which was 3.91 by 2, which is 7.82 meters per second squared. And that's getting us our answer for part 1. For part 2, for the tension, we're going to need to sub back in our value of A into one of our equations. So I'm going to go back to equation 2. T minus 78.4 equals 16a. So T is going to be 78.4 plus 16 times 3.91. And that works out as a tension of 140.96 newtons. So a nice straightforward question in terms of the calculation. The trickiness was the scenario that we were faced with at the start of the question. So this is the question from the 2022 DEB mock exam. So a collar A of mass 5 kg can slide along a rough horizontal rod. It is connected inelastically to a pulley system from which a block B of mass 10 kg hangs freely under gravity by a light inelastic string as shown in the diagram. A horizontal force P of 400 newtons is applied to A, which then moves in the direction of P. The coefficient of friction between A and the rod is 5/7. The three questions are: show on separate diagrams the forces acting on A and B, find the acceleration of A and the acceleration of B, and find the tension in the string connected to B. So the first thing we always want to do is look at our diagram and figure out what's going to happen with regards to movement and acceleration. So our movement, they've been very clear about in the question. They said that A moves in the direction of P. So we have our movement here. So that is our movement, and then therefore B will have to move up. Now, in terms of our acceleration, what we actually have here is a movable pulley. So this piece here is a movable pulley. So it's connected to A, so A is acting like a movable pulley. What that means is we have a movable pulley fixed on one end, meaning we're going to have an acceleration of A and 2A. Because we have two strings here, we can see these two strings. That means the acceleration here is going to be A, and our single string here means this is going to have an acceleration of twice that, which is 2A. Again, the easiest way to make sense of all of this is to think in terms of lengths of string. So for every 1 meter that A moves, it takes 2 meters of string from B. So B will have double that acceleration. So very crude idea, but it's a great way to really think that through. So this is a great example of where we are trying to really find that familiar in a very, very unfamiliar context. Once we have the direction, let's go work with our force diagrams. So let's start with our A. And they tell us that A has a mass of 5 kg. So let's just fill that in. I find having the label, if we have one, and the mass within those particle pieces makes it much, much easier as we go through the question. Let's start adding our forces onto A. All our particles are going to have weight. So here is our weight is equal to mass times our gravity, which works out as 49 newtons. We then have that kind of pulling to the left. Now, when we think of that pulling to the left, that is actually this piece here. But in terms of the shared string, it's going to be equivalent to 2 tensions because there's 2 strings pulling it there. So this is 2T. Just be careful. I know it looks like there's only one piece coming out of A, and that's true. But we need to think of all of that piece that I'm highlighting in blue as one thing. So really the bit that's pulling on it are 2 tensions on that string, and B will have its own tension there as well. We then also have that force P that's pulling to the right, and they tell us that that is 400 newtons. And we also have a reactionary force because of the way that that's hanging on our rod. So that reaction piece is going to be equal to that 49 newtons. So although it's hanging on the rod, there is still a reaction against the weight that's holding it up. It's a bit more complicated than normal, but we can simplify that simply by showing it straight up. We also want to think in terms of, okay, our acceleration or our movement is to the right, and that helps us then apply our friction, because remember that they told us that this was a rough horizontal rod. So that means for us, we also have a friction force that's pulling this over to the left. So that friction force, I'm going to put on the top because of the way that it is hanging on the rod. So our friction here is going to equal to mu times R, which is going to be 5/7 times our reaction, which is 49, which gives us our final answer of friction of 35 newtons. So then we look at our second particle. That particle is B, and B has a mass of 10 kg. It is hanging freely, so we have weight, which is mass times gravity, which gives us 98 newtons. And then we have a tension pulling it up, and its direction of motion is up. And remember that that's 2A. Filling that in is going to help with the next part of the question, which is the idea of working with our F equals ma to figure out what our answers are. So that's going to get you your marks for part 1. So that's our part 1 here. And then for part 2, we're finding the acceleration of A and B. So our A, and then we'll have to double it to get our B, and the tension in the string. So regardless of really what the question is asking, we go to our force equation. So our F equals ma. So for the A particle, our force we take first of all to the right, so that's 400, minus anything that's pulling it to the left, so that's 2T minus 35, and that is equal to our mass, which is 5, times our acceleration, which is our A. This simplifies down to 365 minus 2T is equal to 5A. Remember that anything going with the direction of motion is positive, anything going against it will take as negative. We then have B. B is going to be going T, because that's in the direction of motion, minus its weight, which is 98, is equal to our mass times our acceleration. Be very careful here. That's going to be our 2A, not just A. So this works out as T minus 98 is equal to 20A. That gives us our 2 equations, and we can work with them simultaneously. So we have 365 minus 2T is equal to 5A. I'm going to double my second equation to give me 2t minus 196 is equal to 40a. And what that does is it allows us straight away to add these two equations and remove that t, or the 2t there. So we get 365 minus 196, which gives us 169. That is equal to 45a. Therefore, our value of a is 169 divided by 45, which gives us 3.75 meters per second. That is the acceleration of A. The acceleration of B, remember, is 2A, which is going to be 2 times that, which gives us 7.5 meters per second. And sorry, both of those then should be squared. So part 3 then asks us to find the tension in the string. So all we're doing is we're going back to either of our equations. I'm going to go back to equation 2, that's the one for B, which is t minus 98 is equal to 20 times A. I'm going to fill in that value of A, which is 3.75, and that's going to give us our value of tension, which is 173 newtons. So overall, not a bad question, although initially it may look like it's very complicated. This is all about trying to find the familiar in the unfamiliar.